On March 18, 2018, in Arizona, an Uber self-driving test vehicle was driving at night. Uber had kept a human safety driver in the seat, just in case. Their setup assumed, if the computer messes up, the human will save the situation. A pedestrian was crossing the road. The car's sensors saw the person, but the software didn't know what it was seeing. It kept changing its mind. Maybe it's a car. Maybe it's a bicycle. Maybe it's nothing. And because the system wanted to be sure, it waited. While the software hesitated, the car kept moving. The human looked down briefly. By the time they looked up, a life was lost. The autonomous vehicle industry is trying to answer one very hard question. Can a computer drive more safely than a human in the real world? Current major companies in this industry include Waymo, Google, which runs driverless taxis in limited areas, Tesla, which has driver assistance systems that are not fully self-driving and in which the human is always supposed to stay in control, Aurora, which focuses on autonomous trucks and which acquired Uber ATG after their March 18th incident. Uber ATG, when it started its ambitious journey, tested self-driving cars on public roads. They used human safety drivers and focused on rapid learning and scaling. So what exactly went wrong on March 18th? Uber's car had sensors, cameras, radar, LiDAR. So it saw a person crossing the street. But the software couldn't decide quickly what the object was, and because the system wasn't confident, it did not brake early. This was the first software planning failure. The system was designed to wait for high confidence before acting. Uber had also disabled automatic emergency braking during testing, because sudden braking made the ride uncomfortable, and false positives caused jerky behavior. So the plan was, the software won't slam the brakes. The human will step in if needed. The safety driver was looking down shortly before the crash and did not react in time. This doesn't mean the driver was evil or careless. It means the system relied on a human to do something nearly impossible, avoid sudden danger at night with very little warning. This is another software planning failure, keeping humans as last-second backups for fast automation. So the failure was systemic, not random. It was due to poor software design choices, safety planning decisions, and human automation mismatch. It's easy to say that Uber shouldn't have stopped emergency brakes or that Uber shouldn't have tested on a real road. But there is no way for a computer to learn and evolve as a driver except for practicing on the road, just like a young teenager. Now let's look at some actual solutions that would have satisfied Uber's business goals and also kept safety as a top priority in their learning and experimenting process. Firstly, let's go on to Artis and type in a very specific prompt that says we want to build a driving software that already knows its predictions will sometimes fail when it's on the road. The software must navigate empty and crowded streets and consider all rare accident possibilities whenever committing or not committing an action. Humans should never be its backup for system confusion. Since Uber wanted fast learning and scaling, we also add those requirements into the prompt, but mention that safety comes first at all costs. Self-driving cars are still in the experimentation stage worldwide, so let's choose an internal audience for our software as of now. Next, I go to the analyst and give it a similar scenario of the Uber accident. An autonomous car is driving at night, a human safety driver is present, and the driving software has just observed an unclear object on the path. What does the car actually do in this situation, according to the features recommended by Artis? The analyst lets me know that if the driving software cannot classify an object at night, it will automatically default to conservative, safety-first behavior, despite the presence of the human driver. It also explains the whole process as the software first classifying the object in low confidence and considering the rare possibility of it being a pedestrian. Then, the software reduces the car's speed as a precaution and prepares to stop. And if the unclassified object still remains in its view when it is about to approach it, the software initiates a safe stop while keeping a safe distance. The software does not assume that the human will intervene because it is being tested to be internally safe. All this data is logged, so the monitoring team can easily analyze it later on. The pros of this solution include maximum safety, and the cons include unnecessary stops in rare, confusing cases. But this seems like an intentional trade-off for safety, especially in the testing phase of the software. I ask it what happens if a rare situation that it does not have stored in its database occurs. For example, a car that randomly swerves towards it at an intersection. Based on the recommended features, the analyst tells me that the system will use conservative fallback behaviors, like stopping or yielding to the car. But in the event that it predicts crash as inevitable, it will use emergency maneuvers to minimize harm. Typical methods include emergency braking, evasive steering towards an empty lane or a bush, or doing both if it is safe and effective. The analyst also lets me know that the system will not choose an aggressive behavior, like swerving into pedestrians. Further, after the rare event passes, the system runs a detailed and careful analysis of the road conditions. And if the system's confidence is returned, it continues its test run. However, in the unfortunate event that the system cannot continue, it sends out an emergency alert to the engineering team and shuts down automatically. The critical success factors in the system overview make it clear that scalable learning becomes much more safer through staged rollouts when following the ARTIS recommended module. And the system also learns to drive faster, while still maintaining strict safety standards in a smaller period of time than Uber's original timeline. The prediction module prototype further helps us understand how the software interprets active constraints, like low speed in school zones, and stopping for pedestrians when in close proximity. The software also uses real-time alerts, like object detections on the road, to either stop or adjust its route. If a system can act faster than a human intervention cannot be part of the safety case. That means safety must live inside the software, not at the edges. Uncertainty has to change behavior in real time, reduce speed, widen margins, simplify decisions, or disengage safely. That's not a lesson. That's an implementation strategy.